Hi folks, today we're going to learn about the characteristics of functions, and specifically we're going to learn vocabulary words that are going to help us describe functions so that we can communicate key features of functions to each other. And so there's quite a bit of vocabulary that we're learning today, but we're going to start with intercepts, x-intercepts and y-intercepts. And the x-intercept is where the x-coordinate of a point is the x-coordinate of a point where the graph intersects the x-axis. So where y equals 0, wherever the graph intersects that horizontal axis is the value that we're going to write down there. And then the y-intercept is the y-coordinate of a point where the graph intersects the y-axis, where x equals 0. So let's look at some examples of this using these graphs here and look at what is the x-intercept and what is the y-intercept of these examples. Let's look at the x-intercept first. The x-intercept is wherever the graph crosses the x-axis, which is this horizontal axis here. This blue line crosses the x-axis here at, it looks like x equals negative 1.5. That's something that we're going to go back and confirm later because there's a little bit of uncertainty there of whether that's exactly negative 1.5, and we'll be able to check that later in a moment. But basically what we're saying, if the x-intercept is at x equals negative 1.5, we're saying that there's a point on the graph here at x equals negative 1.5 and y is 0. So we're kind of saying this ordered pair is on the graph. There can be more than one x-intercept. So here on this example, we have intercepts at x equals 1. And another intercept here at x equals 3. And so what we're saying here is that there are intercepts at the points 1, 0 and at 3, 0. In terms of y-intercepts, the y-intercepts occur at where the line crosses the y-axis, this vertical axis here. So looking at where the blue diagonal line crosses the axis, that occurs at y equals 2. And over here we see that the blue curve crosses the y-axis at y equals negative 3. So if we consider the y-intercept, if the graph is of a function, it is not possible to have more than one y-intercept. If you have more than one y-intercept, then your graph is going to fail the vertical line test, and the graph will not be a function. I mentioned earlier that there's a way to kind of go back and check to see if we've actually read the graph correctly, because a graph can help us estimate an intercept, but it's good practice to go back and plug the values into the equation to confirm the intercept. So that's what I'm going to do here. I'm going to go back to the original equation, y equals 4/3 x plus 2. And I'm going to plug this value in for x and this value in for y. And if this is truly a point on the graph, then I will be able to, when I plug in those values, I should get a true statement at the end. So I'm going to plug in 0 for my y value, and I'm going to plug in negative 1.5 for my x value. And when I do this, I find that I find that 4/3 times negative 1.5 gives me negative 2. And when I add 2 to that, I do in fact get 0 equals 0. So I took this point, I plugged it into my equation, and I've confirmed that I've got a true statement. Therefore, this point is in fact on the graph, as I suspected, and because y equals 0 at this point, I've confirmed that this is an x-intercept. We will learn how to algebraically determine x and y intercepts more formally later on in this chapter, but for now, we're just using graphs to estimate the x and y intercepts. The next part B here asks us to talk about where the graphs are positive and where they are negative. So let's go back up and look at our definitions. Where the graph is positive, that's going to be above the x-axis, and where the graph is negative, that's going to be below the x-axis. So if I think about where I'm above or below the x-axis here, if I look at this line, I'm above the x-axis for these values, and I'm below the x-axis for, oh, wrong color. I'm below the x-axis for these values. So what we want is a way to express where on the graph covers that pink region and where on the graph covers the yellow region. And so we're going to define all of our regions on the graph in terms of x. The domain is really important in math, and so we're going to kind of define everything here in terms of x. In fact, the only thing we don't define in terms of x is the y-intercept. So you can see down here when we did our y-intercept, we said y equals 2. There was no x there, but for everything else, we're going to define things in terms of x. So same two graphs. Where are the graphs positive and where are they negative? So I'm going to talk about positive and I'm going to talk about negative. So for the positive values, this graph is positive, kind of not at the intercept here because the intercept is where the graph equals 0, but then I go above 0, I go positive once I'm, for any of these values, above that x-intercept. So I'm going to use this x-intercept value, and I'm going to say that the graph is positive whenever x is greater than negative 1.5. Then for my y values, then for my negative values, when is the graph negative? It's negative, again, this intercept is my cutoff point, my breaking point between where I'm positive and where I'm negative. So x is, this is going to be when x is less than negative 1.5 is going to be the negative region of my graph. Let's do the same thing for the next graph. Where is this graph positive and where is it negative? My graph is positive here when I'm above the x-axis, and then the graph is negative when I'm down here and when I'm down here. And what that means in terms of determining what x values correspond to this, my graph is positive when x is kind of between these two intercepts here, when x is greater than 1, but x is less than 3. And that captures this pink region up here. In terms of where is the graph negative? The graph is negative when I'm to the left of this particular intercept, where x equals 1. So when x is less than 1, the graph is negative. And also the graph is negative when x is to the right of this particular intercept. So when x is greater than 3, the graph is also negative. Let's use the same two graphs and see where are the graphs increasing, where are they decreasing. So let's go back up and see what's happening here on the graph, or the definitions. Where the graph is increasing, it means as x increases, y also increases. Whereas if the graph is decreasing, That means as x increases, y decreases, or there's a negative slope. So looking back at these graphs here, just as a quick reminder or introduction, we haven't formally learned about slopes yet this year, but I'll just draw a few slopes for you here. We will have a positive slope if y increases as x increases, so we'll call this an increasing graph. And then if y decreases as x increases, that's called a decreasing graph. And then you can also have a graph that's neither, where there's neither increasing nor decreasing. It's just a flat graph with a zero slope. So looking at the graphs we have here, where are the graphs increasing? Where are they decreasing? And so I'm going to look at this graph, and as I move to the right, as I increase with x, y also increases across the whole graph, and so this is in terms of increasing. This graph increases for all real numbers. All real numbers, for all values of x, this graph is increasing. So that means in terms of decreasing that there are no regions where this graph decreases. So we'll just say never. Okay, never decreasing for this graph. On the other hand, if we look at this graph here, this graph starts off as increasing. As I move to the right, the y value also increases. But then at this point here, at this peak point, we turn around and as I move to the right, the y value decreases. So here we do have a switch, we have a change. This graph is increasing up until that peak point, and that peak point happens at x equals 2. So when x is less than 2, the graph is increasing. And then when x is greater than 2, the graph is decreasing here on this side of the curve. And right at 2, the graph is neither increasing nor decreasing. It's neither, because the graph is kind of level at that point. The next thing we need to learn about in terms of describing graphs is describing their end behavior. So let's scroll back up and see about the end behavior. End behavior describes what happens to y as x approaches positive infinity or negative infinity. So we're describing what happens at the very edges of the graph. And so what this means here is we're going to say as x approaches positive infinity, y approaches what? We're going to kind of fill in the blank here. And we also need to investigate as x approaches negative infinity, y approaches what? So let's look at graph A and see what we have here. As x gets bigger and bigger and bigger, as we extend in the positive x direction, I see that the y value is going to continue to go up and up and up. Therefore, as x approaches positive infinity, y approaches positive infinity. The y value keeps on getting larger and larger forever. On the other hand, as x gets really, really small, more and more negative, then what happens to the y value? The y value goes down and down and down even more on forever. And so y will approach negative infinity as x approaches negative infinity. So kind of filling in the blanks here, we're going to say as x approaches positive infinity, y also approaches positive infinity. And as x approaches negative infinity, y also approaches negative infinity. For graph B, we're going to need to do the same thing. So we're going to have to come up with two statements. As x approaches positive infinity, what happens to y? And as x approaches negative infinity, what happens to y? So let's go up at the graph and see. As I move to the right on forever, what happens to y? Y keeps on going down and down and down. So as x approaches positive infinity, y approaches negative infinity. Similarly, as I move in the negative x direction, as I get smaller and smaller in this direction, more and more negative, then y also gets more and more negative. So as x approaches negative infinity, y approaches negative infinity. So in both of these cases, positive infinity for x or negative infinity for x, y approaches negative infinity in both cases. Now, I don't want to leave you with the impression that end behavior is always towards positive infinity or negative infinity. That is not the case. And I have an example here, this note here to kind of draw attention to that fact. The end behavior does not have to approach positive or negative infinity. And so in this example, as x approaches negative infinity, y in fact does approach positive infinity. But if you look at this direction, as y approaches positive infinity, y is getting smaller and smaller and smaller, but it's approaching zero. Y never actually reaches zero, but it approaches zero. So you can have graphs like this that approach a number instead of approaching infinity. All right, so let's try to put it all together at once. Pause the video if you need to and take a moment and try to come up with the x-intercept or intercepts, the y-intercept, positive or where the graph is positive, where it's negative, where it's increasing, where it's decreasing, and what the end behavior is. So first of all, the x-intercepts. If I'm looking here at where the graph touches the x-intercept, I have values here at these two locations, and that is where x equals 0 and where x equals 3. For my y-intercept, where does this graph intersect this vertical y-axis? That's also this same point. One of my x-intercepts is the same as my y-intercept, and that's where y equals 0. Where is this graph positive? The graph is positive any place I'm above the x-axis, so that's this whole region here that I've highlighted in pink. And that happens. Remember to use the x-intercepts as kind of your break-off points for where you're positive or where you're negative. Here, this pink region is every place where x is less than 0. So the graph is positive when x is less than 0. See how I base that off of one of my intercepts? And x is also positive when I'm between 0 and 3. So when x is greater than 0 but less than 3, this graph is also positive. In terms of where the graph is negative, the graph is going to be negative just in this region here, where we're past this intercept of x equals 3. So when x is greater than 3, that's where the graph is negative. So for positive and negative values, or for positive and negative regions of the graph, be sure you're referring back to those places where the x-intercepts were. Where is this graph increasing? Remember, increasing is going to be where the slope kind of looks like that, and decreasing is going to be where the slope kind of looks like that. So looking at my graph, where is this graph increasing? It's only increasing here up to this point, from the 0 up to this peak, and the peak seems to happen at 2. So that's what I'm going to write down. I'm going to say the graph is increasing when x is between the 0 value and the 2 value. Where is this graph decreasing? It's decreasing before the 0, and then again after the 2, because that's when my slope goes more in this direction, the decreasing direction. So how do I express that? Well, these are the regions where x is less than 0 and where x is, let's see, that peak happened at 2, so where x is greater than 2. In terms of my end behavior, remember you kind of want to write this a sentence out of this as x approaches positive infinity, y does what? And as x approaches negative infinity, y does what? So looking at the graph, as we approach positive infinity in the x direction, as we go more and more this way, the graph goes more and more downward. So y is approaching negative infinity. And as x approaches negative infinity, as I move more and more to the left, the y value gets bigger and bigger, goes up and up. So y approaches positive infinity. Lastly, let's look at a real-life problem and how we can kind of think about two graphs, compare two graphs on the same coordinate plane. So, two robots on the same asteroid move by hopping. This graph shows the path of robot A's first hop. Robot B's hop has a similar shape, so it's going to have a curved shape, but different dimensions. It reaches its peak height of 48 feet. So a peak height of 48 feet, which is going to be just shy of 50, about here, when it has traveled a horizontal distance of 30 feet. So a horizontal distance here. So the peak is going to be right about here. Now, if that's the peak of the jump, try to kind of draw a curve here. If that's the peak of the jump, then there's more to the jump. It's going to continue to extend symmetrically. Look at the peak of the jump here. That's kind of like the halfway point between the start of the jump and the end of the jump for robot A. And so I want to draw a similar shape where this is my halfway point, and then since I've gone 30 feet here, I need to go an additional 30 feet on my way down and curve back down to 60. Mine isn't a beautiful parabola curve, but it will do for the purposes of this activity. Okay, it says, oh, I've already done the first thing. Sketch robot B's hop on the same graph. So that's what I did here. Red is robot B. And now I'm going to compare the horizontal distance traveled by both robots. Okay, so robot A traveled, a little hard to tell because it's between values here, but that looks like traveled 45 feet. And robot B, we know for sure, traveled 60 feet. Okay, so robot B traveled further horizontally. But if we compare the vertical heights reached by both robots, I can see robot A, robot A seems to have reached halfway between the 50 and the 60. So if I'm halfway between 50 and 60, I'm going to call that 55. So robot A got to about 55 feet. And robot B got to just this value that we were given in the problem, got to 48 feet. So here we have, we've used a graph and plotted two graphs on the same coordinate plane to kind of gather measurements so that we could compare these two robot trajectories. I hope this helped.